Hello everyone, and thank you for joining us for today's Surface Measurement Systems webinar. Today we will be exploring the topic of advanced sorption technologies for porous materials characterization, and we're very lucky to be joined by Connor Hewson from Surface Measurement Systems to discuss today's topic. Just to let you all know, there will be a live Q&A session at the end of today's presentation. So please, at any point during the session, submit your questions in the Q&A panel, and these will be answered by Connor at the end of today's session. So once again, we will have a live Q&A session. Please do submit any questions as they come up throughout the presentation, and these will be answered at the end. We're very lucky today to be joined by Connor Hewson. Connor is a senior product specialist at Surface Measurement Systems, where he manages the DVS Carbon, DVS Vacuum, and Vapor Pressure Analyzer family of products, with a focus on applications of these instruments for porous materials. Connor obtained his master's degree in chemistry from Nottingham University in 2019, and his research ranges from carbon capture, heat pumps, indoor air quality, co-sorption, and more. So without further ado, I will now hand over to Connor to begin the presentation.
Thanks for that, John. Can I get a confirmation that you can see my screen, John?
Yes, yeah, all good.
Okay, great. Yeah, thanks everyone for being here today. John's given me a really nice introduction. Yeah, so just one more time, I'm Connor Hewson. I've been at Surface Measurement Systems for about 4 years. We're going to be talking about using porous material, how we can characterize porous materials using sorption instrumentation. We'll be focusing on a lot of sorption instrumentation sold by Surface Measurement Systems. But before we begin, let's start off at the beginning. We'll start off with an agenda for today's presentation. So the first few slides, I'm going to introduce Surface Measurement Systems. I'm going to say who we are, what we do, where we are. I'm going to do a brief introduction into some science intro. So looking how we can use sorption to characterize material generally, and zoom in on some of the instrumentation that Surface Measurement Systems provides. Then, once we have an intro into how all of the instruments work, we are then going to go into some case studies. The first half is going to be case studies mainly focused around carbon capture. Then we're going to be looking at a MOF co-sorption case study, stability in water and how well it can work in co-sorption scenarios. We're then going to be looking at zeolite 13X for applications in carbon capture for post-combustion streams in the presence of contaminants like water, and SOx and NOx. And our final chapter is going to be looking at instruments for VOC capture. This is going to be looking at managing indoor air quality using porous materials, specifically 13X and activated carbon. And then we're going to be looking at MOF-based sensors for VOC detection in reduced pressures, like in space exploration applications. So, who are we? Me, John, and a few other colleagues that are on this call right now, we all work for Surface Measurement Systems. We're a company that are founded in London. We are located in Wembley and established in 1990. Our CEO is Professor Darryl Williams, and he's a professor at Imperial College London, and he was the developer of the dynamic vapor sorption technique. So that was the first instrument that was sold by Surface Measurement Systems, was a dynamic vapor sorption instrument, and that's going to be featuring in a lot of our case studies today. So here's a quick picture of the team that was taken in 2023, and you can see me right at the front there with some of our colleagues that are on the call today as well. So after today's session, we'd love for you to get in touch, to engage in the Q&A. If you have any questions, feel free to ask at the end or drop us an email, and we'll be happy to see how we can help, offer out our services, so on and so forth. So, who are we? We are a manufacturer of scientific instruments which are mainly used for solid characterization. We are based around the world. We have manufacturing, laboratories, contract services, and service operating out of Europe, mainly out of the UK. We have some offices in America, in Pennsylvania, where they have production, a lab, and service and sales operating out from here. We have SMS China, which is operating on a sales basis directly in China. And then we have laboratories in India where we do sales, service, contract measurements, which is located in Hyderabad. So we've sold over 2,000 instruments worldwide. We've been in 6,000 publications. And our absorption applications range into a wide variety of different areas, with our main application area being in pharmaceuticals, and our second largest being in porous materials. So things like MOFs, zeolites, polymers as well. And we can see a bunch of other industries which use absorption to characterize their solid materials. But we are mainly, in today's talk, going to be focusing on the porous materials and how they can be used for characterization. So here is just a brief slide of some of the instruments we sell at Surface Measurement Systems. Now, unfortunately, today's presentation is only going to be 90 minutes, so we won't have the ability to go into detail on every single one of these instruments, but we will be able to go into detail on a select few. Now, the ones that are most geared up for porous materials are going to be those such as the DVS carbon, which is for water and CO2 capture, the breakthrough analyzer, which is going to be for multi-component analysis, so water plus organics or water plus CO2, or something more fundamental like the DVS vacuum, looking at kinetics and working capacity, particularly good at single component reagents. So at Surface Measurement Systems, we offer a range of instrumentation. Our primary goal is to sell instrumentation, but we also offer support work, contract-based work, and we're happy to collaborate in order to do co-authored publications. So please get in touch if you have an inquiry about an instrument or an inquiry about a collaboration or doing some experiments on some of our kit. So let's go into an introduction for absorption as a whole and why we would want to use absorption to characterize our materials. So we are using absorption. We are using molecules, flowing them over a material so that we can probe that material. So here we are flowing over our gas molecules or our vapor molecules over our sample and over our surface. As these gas molecules and vapor molecules flow over the surface, they will interact with that surface. They can either adsorb onto the surface of the material, and we would call that adsorption, or they could migrate from this surface into the bulk of the material, in which case this would be bulk absorption. And we would see these probe molecules leave the material as well. When we are flowing over these gas and vapor molecules, they are in a dynamic equilibrium with our surface. So our gas molecules are guests on the surface and they absorb and desorb. We're in a dynamic equilibrium with our surface. So these guest molecules, as they interact with their surface, we can gain an understanding of the surface properties, the strength of that gas-solid interaction. We can measure the total uptake, the kinetics of the uptake. And all of this is done in order to yield useful information about the sample itself. So we can also get an idea of the strength of this interaction. If it is a relatively weak interaction and quite reversible, we would say that this is physisorption, a process which happens spontaneously on the surface, and one where the bonds are relatively weak and reversible. We could also go through chemisorption, where our water molecule may strongly bind to the surface, form something like a hydrogen bond with its surface, or with make a solvate with the surface, a hydrate with the surface, and chemically change the properties of that surface to make a strong chemical bond, in which case we would see a more irreversible interaction. We can also see differences in adsorption into the bulk. We can either have bulk adsorption, where our material is bound between polymer chains, in between pores of the material, or we can get adsorption, which changes the entire chemical structure of the material, which is going to be having a lattice change, where we have something like hydrates or formates forming, or sorbates forming. Now, we're going to be mainly focusing on porous materials. These porous materials generally are going to have these high surface areas, and these high surface areas allow for a very high contact point for our probe molecules to interact with the surfaces of the porous material. By virtue of having this very high surface area, they can have a high absorption capacity and high working capacity for some of the things we want to absorb onto these porous materials. We can also have some porous materials which have functionalized surfaces. These functionalized surfaces may lead to a stronger interaction with things like water or CO2 on its surface. And often with some of these functionalized materials, we are having both of these interactions happening at once, both physisorption and chemisorption happening with our surface. So in all of the case studies we're going to be looking at today, we're going to be looking at porous materials, materials generally with these well-defined pores in their surfaces, which have a well-defined volume within, where the pore size is well-defined. We can have a pore size which limits the diffusion of some absorptives into the material, or we can have pore sizes which are small enough to allow for condensation within their pores to lead to these high uptakes. We're mainly going to be looking at some case studies with zeolites and with metal organic frameworks, but a lot of these applications we're going to be looking at can be applied to many different types of porous materials, things like clays, things like silicas, or instead of a MOF, we can have a COF or a HOF. So why do I want to use a porous material in the first place? Porous materials are generally useful because they have a few good assets in their toolbox. Porous materials generally, because they have a high internal surface area, they have a high working capacity. Now, when I say high working capacity, this means that this material can absorb a lot of this sorbate. We can absorb a lot of toluene, we can absorb a lot of CO2, or we can absorb a lot of water. So they have a high working capacity. They can absorb a lot of my sorbate, which is good when we're trying to make a process for capturing that reagent. So I can get the most efficiency from having this high capture capacity. Now, there's no point in having a material with a high working capacity unless we can absorb our reagents quickly. So we need our material to have the right kinetics. It needs to be able to absorb a decent amount of CO2, a decent amount of VOCs in a time frame where we can actually be effective in our process. So we need to find a good porous material or solid adsorbent which can capture a lot of our absorptive and capture that absorptive relatively quickly. We then need our porous material to display a positive selectivity, which effectively means that our porous material will selectively absorb our primary adsorbate, the thing we want it to absorb, versus some of the other reagents that may be in that gas stream. So I want my porous material to show some selectivity to these reagents versus some of the agents I don't want it to catch. Now, this is going to be an area where we focus on heavily today, is looking at how we can use surface measurement systems instruments to qualify how well we can, how good our porous materials are at selectively absorbing one reagent over another. And we're going to make an assessment in what these reagents have on the impact of these porous materials. So one of the useful things about our porous materials, particularly things like zeolites and silicas, is their ability to regenerate. They're very stable at high temperatures. This means I can put in a lot of thermal energy. As I put in a lot of this thermal energy, I'm desorbing a lot of the things I've previously absorbed, and my material will maintain its working capacity and will maintain its absorption kinetics. So our porous materials are good because they absorb a lot, they absorb it quickly, they can be selective, and they have a long lifetime because they can be very stable. We need it to have the right thermal properties, so it needs to be able to conduct heat relatively efficiently. It needs to be able to conduct that heat so it can be reactivated for the next use in its lifetime, the next capture cycle. And we need to think about some economic costs. So there's no point having a porous material which is outrageously expensive. Otherwise, you will not be able to use that material on a large enough scale to actually be economical or make an impact on the process you're trying to apply it to. Then we need to think about things like morphology, structure, lifetime, and some of these other areas. But it's important to keep in mind that when you're looking for a porous material to apply to a process, all of these considerations need to be taken into account. So how do we evaluate novel solid sorbents? The reason I've put this slide on the screen is to really show that there are a lot of ways that we can calculate and assess adsorbents for their selectivity. We can use single component isotherms to give you an idea on their working capacity. We can then use these single component isotherms to calculate some form of selectivity and work out whether or not one reagent will be competitively absorbed over another. But unfortunately, really what these screening processes do is they may give you an indication. They may give you a starting point. However, these models are no replacement for actually doing the experiments yourself. So we can make as many assessments using a model, using calculations of their single component experiments, but that is no replacement for doing these experiments in real life co-sorption settings or in real life industrial application scenarios. So putting in water, putting in CO2, and seeing how that material maintains its working capacity in the presence of these two. So doing the experiments instead of relying on some of these models. And that's really going to be what we're focusing on in some of these case studies, using instrumentation to assess these materials in these real world conditions to see whether or not these models that we predict actually match up to some of our experimental data. So that's an introduction to the science done and dusted. Now we're going to move on to some of our instrumentation. We're going to give an introduction to what surface measurement systems instrumentation is like and what it can do. So I've repeated this slide so that we can see that some of our instruments work on the fundamental level. These are going to be good at doing single component isotherms, things like the DVS vacuum and the inverse gas chromatography surface energy analyzer. These are good at the fundamental properties, looking at your absorption capacities, your enthalpy of adsorption, surface area, surface energy. So these work out the fundamentals of a material and are very good when you have a novel material and you need to work out the single component isotherms of these materials or the fundamental properties of those materials. Now, once you are happy with the fundamental properties, you have single component isotherms, you have an idea of kinetics, you know the surface properties and functionalization, then we want to move on to how can I move that porous material into a process? If my material is good at capturing carbon, carbon dioxide, I may want to assess its carbon capture performance in the presence of water or SO2 or NO2 and see whether or not it can still absorb CO2 in the presence of some of these other reagents. And that's what we call real-world conditions, actually assessing some of these porous materials in industrial relevant conditions, in atmospheric conditions, and see whether or not some of the things I modeled fundamentally can actually be upscaled to real-world conditions. And then I want to go into even more detail. I want to go closer to the process. So now I want my porous material to be packed into a bed. I want to get an idea of the bulk properties of that material. And I want to get true multi-component adsorption. And that's where things like breakthrough analysis may come in into play. And we're going to talk about a lot of these instruments in a bit more detail. So our most popular instrument range is dynamic vapor sorption. So dynamic vapor sorption, which has been shortened to DVS, this is a gravimetric technique. Now, when I say gravimetric, what that means is this is an instrument where we have a balance involved. This balance is the heart of the system. This is the primary detector within the system. The purpose of this balance is to load a sample onto one side of the balance, flow over our gas or our vapor, and see how the mass of that sample changes. So I'm looking at gravimetric data. I want to see how the mass is evolving as a function of time and as I change the temperature or I change the concentration of something I want to measure. So this gives us a lot of benefits having a gravimetric technique. Our gravimetric technique has a very sensitive balance. Now, because this balance is very sensitive, we can use incredibly small amounts of sample. And we can measure incredibly small mass changes in that sample. So if I have a precious porous material that's taken me my entire PhD to synthesize that porous material, I can make a good assessment of adsorption isotherms in a non-destructive means. The good thing about adsorption technique is often these interactions with the gas molecules are reversible. So when I absorb water, it may desorb afterwards. So it's a non-destructive form of analysis, which is another benefit of using DVS or BTA to characterize your materials. So a lot of the data we're going to be looking at in these later case studies will be gravimetric, DVS data. And I'll show you some case studies where we can see mass change as we change the concentration. So we have a lot of DVS products. We have some which work just with water, and we have some which work better for co-sorption, so letting in water and an organic vapor, or water and CO2. And all of these have their different strengths. Some work for water and organics for a single sample and can be hyphenated with different techniques like camera and Raman spectroscopy. Some can work in a high throughput manner, where we are now doing 5 samples all simultaneously to get this high throughput screening of these materials. Some work with water and carbon dioxide, so very similar to what we saw up here, but now working with a slightly different co-sorption scenario and a different application. So we offer a wide range of gravimetric solutions which work with slightly different sorbtives. So gravimetric data, what does it look like? So I'm going to be showing a lot of figures showing some data which are going to be have the same general look and feel. Now, most of the data I'll be showing are either going to be kinetic data or isothermal data. Kinetic data will be showing how the mass of the sample is changing as a function of time. So we're making an assessment of the kinetics, the speed of desorption or the speed of sorption. Now, I'm looking at time and how the mass is changing over time. And then I can also see how concentration is changing. So this line in blue here is a representation of relative humidity. And we can see as I started my experiment, the mass of the sample went down because I'm drying the sample. Now, after a fixed amount of time, the concentration of relative humidity increased in a stepwise fashion, and the mass of the sample increased. The mass of the sample increased because it was absorbing water. So we can see it's fast at the beginning, and then begins to equilibrate at the end. So we can see the mass is no longer changing at this relative humidity, at which point the method moves on to the next relative humidity step. And in this next step, we can see the same pattern emerging. The mass of the sample goes up and it equilibrates. The mass of the sample goes up and it equilibrates. And we can do this with relative humidity increasing, and I call this the sorption branch of my isotherm, or we can do this in a decreasing fashion, and this is the desorption part of my isotherm. Now, kinetics data is resolved by time. But in an isothermal data, now we are going to remove that kinetic information. I now am only going to plot weight versus relative humidity. So I'm just going to take the final mass equilibrated at every concentration. So the mass of the sample at this humidity step, the mass of the sample at this humidity step, the mass of the sample at the end of this humidity step, and I'm going to plot them onto this isotherm. Now, isothermal data is very commonly accepted in the sorption industry, and making these isotherms is beneficial because the shape of the isotherm, the characteristics of this isotherm tell you a lot about the material. I can tell whether or not a material, or I can have a good indication and a good guess whether or not a material is microporous, mesoporous, macroporous. I can give an indication whether or not the strength of the interaction between the adsorbent and the adsorbate is strong or weak based on the characteristics of this isotherm. I may also give an idea of how much bulk adsorption is going on with this material by looking at the hysteresis. The hysteresis is this gap in the middle, the difference between the sorption equilibrated masses and the desorption equilibrated masses. So the isotherm tells me a lot of useful information about my material. So gravimetric data is going to be a large part of these the presentation, but we're also going to be talking a lot about breakthrough analysis. And that's breakthrough analysis is what BTA stands for. Now, this is another technique that's sold by surface measurement systems. This is a chromatographic technique. Now, this means this sample no longer has a balance. We are not measuring a mass change within the sample. We're now making a bit more of an indirect measurement of sorption. So instead of looking at the mass change of the sample, I am now going to be looking at how long does it take for my gases that I am detecting and letting into a system, how long will it take for that gas, that vapor, that mixture of gases and vapors to flow through my column and reach my detectors. And that's what we're looking for. We're looking for the time it takes for my gas mixture to break through a packed column of the sample I'm interested in. So this is an interesting technique because now this is a different way of measuring adsorption that has a few added benefits which we don't see within within DVS. Within DVS, typically we're working with small amounts of samples, so 10, 20, 30 milligrams. In breakthrough analysis, we're working with a bit more sample. This can be up from 50 milligrams to gram scale. We may want more column to pack and fill this column bed. Now, breakthrough analysis is great at looking at multi-components. We can look exactly how much water and exactly how much CO2 is being absorbed when I do multiple gas mixtures. But we will get to that a little bit later when we go on to a case study with breakthrough analysis. So here's a quick introduction to how our breakthrough analyzer looks. We have a variety of different gas inlets. We then have a different few flow paths, whether we can let in our gas mixture and vent it, or we can introduce it to our sensors, or we can introduce it to our columns. We can pass it over column 1, filled with sample A, or column 2, filled with sample B. And then it hits an array of sensors. The good thing about Breakthrough Analyzer is it's got a lot of different sensors which are specific to different sorbates, vapors, gases. We have a sensor sensitive to relative humidity. We have a sensor sensitive to CO2. We have a variety of photoionization detectors. These are good at looking for VOCs, organic vapors. And then we have TCD sensors, so thermal conductivity detectors. These are good at looking at binary gas mixtures. So for example, something like helium and CO2, hydrogen and CO2, methane and nitrogen. That's what this detector's for. Now this will be looking at the detection point of all of the gas mixtures I let in. So breakthrough analysis has got a lot of very specific sensors for measuring very specific things, gases, vapors, things like that. In the gravimetric systems, we have a balance, which is good at measuring total uptake and looking at measuring how the mass of the sample evolves. So in a lot of the presentation, in a lot of the case studies we're going to be talking about today, we're going to look at both data, gravimetric data and breakthrough analysis data. But they are measured in slightly different ways, and just bear that in mind when we're looking at some of these case studies. Now, this is generally what breakthrough analysis data looks like. We're going to have time zero when I start letting in something like relative humidity over my sample packed in this column bed here. Now, for the first 30 minutes of my experiment, none of this water has actually escaped the column. And that's because it's slowly saturating the column. Some of it absorbed here, some of it absorbed here, and none of that water has actually broke through the column yet and found its way to the end. After about 35 minutes, we finally have a scenario where some relative humidity is actually reaching my detectors at the end of the column. And that's why our line is going up here. We can see we are plotting time versus a concentration. So finally, I'm measuring a signal at some of the sensors at the end of the column. Now, there comes a point where I very quickly start to saturate my sample, concentration increases very quickly, and then we come to a time where my breakthrough equals 1, which effectively means the concentration I am letting in is matching the concentration I am detecting on the outlet. And this is when we deem this to be fully broken through. And what we get from breakthrough data is the area under this curve when we translocate this time equilibrated down here. If I plot the area under this curve, that's going to give me the amount absorbed. Now, the benefit of a breakthrough analyzer is doing this while we're letting in two things at once. So I can let in CO2, measure the breakthrough of that CO2, and I can let in water and measure the breakthrough of that water. Now, analyzing both of these reagents at once, I can get the absorbed amount of both water and CO2 in a co-sorption scenario. Now, we're going to come back to that into some of the case studies we will see later. So let's move into some of these case studies. The first few case studies are going to be focused around using surface measurement system products for carbon capture. We're going to be using these products to see how various different materials can be used for carbon capture applications. So I think everyone in this meeting right now can be very much aware why it is important to capture carbon dioxide from the environment. As we know, global warming is going on at an increasing rate because every year we are letting out and emitting CO2 into the atmosphere. CO2 is a very effective greenhouse gas, making the atmosphere heat. So we are heating our world, and that has a lot of non-beneficial effects for us as humankind and for the environment. So there have been lots of government legislations that have been put in place in order to decrease emissions. But that isn't good enough. In order to reverse the influence of global warming, and in order to scale up as an economy, we need to be able to capture CO2 from the environment to reverse these effects. So we need to develop materials that can harvest CO2 from the air in direct air capture, or put them in the exhaust of coal plants and capture CO2 from its source before it is emitted into the environment. So there's a few different ways that we can capture CO2 from our environment. We can do this directly from the air. Now, this is a good idea because essentially that CO2 source can be infinite. We are capturing CO2 from anywhere in the world where we can put these outside. These conditions generally mean that you will only have to compete with things like relative humidity. However, our concentrations are very, very low. The atmospheric concentration is around 420 ppm, a very small concentration. And that means there are some challenges. That means generally that carbon capture will be slow, but it has the benefit of being a relatively infinite source of CO2. And you only have a small range of temperatures that you're going to have to compete with. So we can make a carbon capture to do this from the air. We can also make a carbon capture material which is capturing under post-combustion conditions or point source. Now this has got the benefit of CO2 concentrations being a lot higher. So we would see concentrations of CO2 somewhere between 5% or 40% by volume. So we could make a more efficient carbon capture process because there's more carbon to capture. However, we have a lot more to compete against. We're going to be working at a lot higher temperatures, and we're going to have a lot of secondary contaminants. Some of these contaminants might be things like water, which can be very high in volume. So there's a lot of water to compete against. Or some of these contaminants may be smaller in concentration, but they can be more poisoning like agents. So things like NO2, SO2, ammonia, they can strongly bind to our carbon capture adsorbents and irreversibly bind to them, causing them to slowly degrade over their lifetime and become less efficient at capturing carbon. So we're going to be looking mainly at this area and these case studies for evaluating materials for capturing carbon in post-combustion conditions. So in both direct air capture and in post-combustion, we're generally competing for absorbing CO2 versus water. So why is water of such concern to these porous materials being used in carbon capture processes? Well, a lot of water generally binds to these materials, and they offer competitive adsorption, which effectively means if my porous material previously had CO2 adsorbed on it, as the water comes in, it will preferentially bind to water over CO2, and the water that was previously there will be displaced. So these materials may prefer to absorb to water as they would CO2. Water also has the benefit of it being able to exist as a liquid. That means water can condense within the pores of these materials and be very thermodynamically stable as that water within some of these things like mesopores. That pore filling mechanism, that condensation, can drive off some of the things that were previously absorbed in the pore of that porous material. And water is a very effective solvent. It may cause structural changes to some of my MOFs, cause degradation of some of these structures within the material. Water can also behave as a ligand to some of these metal centers, causing that structure to collapse. This is also because water is a very good solvent. We can in fact cause materials to dissolve within the water it is absorbing, where we get our MOF to deliquesce. And so water can have a very negative effect on some of our porous materials. And we're going to be looking at using our instrumentation to assess how much of this is happening. Now, it is important to comment that water can sometimes be a benefit. In things like amine chemistry, the presence of water actually enhances amine functional groups' ability to capture CO2. So sometimes water can be a benefit to your process, particularly if you have functionalization of some of your materials. Now, even if water isn't interactive directly with our porous material in a competitive or in a collaborative sense, water may still be present, and it can be a thermal sink to my process, which effectively means that most of the heat going into my process, which I want to just be reactivating my porous material, is instead going on desorbing water. So it's a thermal sink to my process. So we're going to go into our first case study now. Now, this is going to be using a novel MOF for post-combustion CO2 capture. So MOFs are metal organic frameworks, which are effectively one metal center, which is having a few organic-based linkers which link between these metal centers. Now, this means we can have a well-defined pore size, which is tuned by selecting what ligands I'm actually using. By tuning the metal that I have in here and the linker that I have, I can also introduce some chemical functionality to these porous materials. So metal organic frameworks are porous materials with well-defined pore sizes, tunable pore sizes with some functionality that we can introduce. Now, here is a company called NovaMOF, which make a wide variety of metal organic frameworks. They've designed a novel porous material, or MOF, for carbon capture applications. And they did a joint study with us where they took this novel MOF, they put it in some of our instruments to assess how good it was at capturing CO2 in post-combustion conditions. So we started off with the fundamentals. We wanted to see what is the working capacity of this novel MOF in capturing CO2. So we did some CO2 isotherms. This is where I kept the temperature constant. So I was looking at how much CO2 was absorbed at 25 degrees C and how much CO2 was absorbed at 40 degrees C. And we can see here I am looking at how the CO2 concentration is changing from 0 bar to 1 bar and slowly going up in the step size in between. And I'm looking at how much did the mass change as a percentage. So here we can see at around 0.2 bar, the mass had changed by around 6 or 7%. And we can see by the time we reach around 0.95 bar, our uptake at 40 degrees C is around 15% change in mass. And at 25 degrees C, that's around an 18% change in mass. So I can see that this material has a good working capacity. It can absorb a lot of CO2. Now that's good for my process. It will be efficient at capturing carbon dioxide. I can also look at the kinetic data. So how quickly did it absorb CO2 during the experiment? And I can see this as I was changing the concentration stepwise. So I went from 1% CO2 to 2% CO2 to 5% CO2 to 10. I can see how did the mass of the sample react at all of these concentrations. And really the takeaway point I want you to make from this slide is it was reaching equilibration relatively quickly. So really, our material seems to absorb a lot of CO2 and absorb it quickly. That is our first big win for this novel MOF material. I then want to see how stable is this material for carbon capture. So what we did was a number of different CO2 cycles. So 0 to 100% CO2 concentration over a number of cycles. So I did 0 to 100, reactivate, 0 to 100, reactivate, so desorbing the CO2 I previously absorbed, 100, reactivate, and here we can see the mass of the sample. So it's going up, reaching equilibration, going down, going up, reaching equilibration, going down. And I can see this material has a very consistent performance. It's very regularly coming back to the same equilibrated mass. So this means it isn't degrading between absorption cycles. And that's another big win for this material. This means it can absorb CO2 reversibly and maintain that capacity over many absorption cycles. And if I take a closer look at one of these first cycles, this material was able to really almost reach 90% of its saturated capacity within just 5 minutes of exposure to CO2. So again, further proving this material can absorb CO2 quickly. So now let's make an assessment on water adsorption. So this material, we also need to make sure it can absorb a good amount of it can absorb water in a stable fashion. So we did a water sorption isotherm at 5 degrees C, that's shown in the black line. A water sorption isotherm shown at 25 degrees C, that's shown in the blue line, and one at 40 degrees C. Now, what we can see, this material does absorb water, but we could say its water absorption capacity is relatively low, especially at these low domains. So less than 40% relative humidity, our water absorption capacity is relatively low. That capacity begins to kick up at some of these high relative humidities. So it becomes much higher at these, the uptake is higher at higher relative humidities. However, there is something we notice about this material, the fact that when I go to certain relative humidity steps, the mass of the sample seems to go down, which is suggesting that the material has a small amount of instability. It will collapse in the presence of relative humidity. So this material appears to show that it may not be very suitable at certain relative humidities. So at 25 degrees C, that relative humidity where we show some instability is from around 80% RH plus. At 40 degrees C, that happens at a slightly lower relative humidity. So I wanted to see what this sort of impact has on this material's behavior for carbon capture. So I did a similar experiment to one we saw before. I was doing some CO2 cycling. So here we can see I'm going from 0% CO2 to 100% CO2, 0% CO2 to 100% CO2. I'm doing the same cycling and getting a good performance. In between some of these cycles, I did a relative humidity step. I'm now letting in something like 25% relative humidity. I'm desorbing that relative humidity and I'm doing my CO2 cycles again. And what I can see is after absorbing 25% relative humidity and desorbing it, I can maintain the same CO2 capacity I was in the previous cycles. I then do the same again, but with a larger relative humidity step. I'm doing this with a 50% relative humidity step. And now what I see is again, slightly higher uptake, desorb, but I maintain my CO2 capacity. And now we're going to a larger step, 75% relative humidity. Uptake is much, much higher for that water step. And I can see when I do my CO2 cycles again, now my capacity has decreased from around 18% to closer to 12%. So humidity has had an impact on this material's ability to do carbon capture. So this material was showing that it had a good CO2 working capacity and a good CO2 absorption kinetics, but it needs to be kept at relative humidities lower than certain thresholds based on the temperature. Now, we went on to look, rather than looking at the single component absorption, which is just CO2, or just relative humidity. Now we want to assess this material in co-sorption scenarios. When I say co-sorption, that effectively means I let in CO2 and I let in humidity both at the same time. So I did this with 10% CO2, and this was my uptake for 10% CO2 just on its own. For relative humidity, this was the uptake for relative humidity just on its own. And then using the DVS carbon, I did a step where I let in some relative humidity. The sample then equilibrated. And while that relative humidity is still flowing over the sample dynamically, I introduce a flow of CO2 as well. So what I'm letting in is two components simultaneously, and I'm measuring the multi-component uptake. So this is the total uptake being measured in a gravimetric system. So what I can see here is in this multi-component step, when I have humidity and I introduce CO2, the mass goes up. So it appears as if I'm absorbing CO2 in the presence of relative humidity. Now, something interesting is when I look at this number here, 11.25, this appears as if it is an addition of the single component CO2 and the single component relative humidity. But unfortunately, in the gravimetric data, I am only looking at total uptake. I'm looking at the mass change of the sample. Unfortunately, in a gravimetric instrument, you cannot distinguish how much of this total uptake is water and how much of this total uptake is CO2. What we measure is total uptake, the mixed uptake. I don't know exactly how much of this is water and how much of this is CO2. And that is where breakthrough analysis comes in. Breakthrough analysis is able to look exactly how much of that total uptake is water and how much of that total uptake is CO2. So now I can work out from this total uptake, 4.46 of this is CO2 and 5.69 of this is relative humidity. So this is a huge benefit. We have a porous material which is able to maintain some of its CO2 capture performance very close to if water wasn't present at all in the presence of relative humidity. So Nova MOF were able to make a porous material, a MOF, which was able to capture carbon dioxide in the presence of relative humidity. However, we need to build a carbon capture process which keeps the relative humidity below 50% to afford full CO2 uptake capacity. So we use the DVS carbon to look at the single component and some multi-component. This material absorbed CO2 quickly, it absorbed it to a high absorption capacity, and we can build a process, a carbon capture process, which can utilize this MOF successfully. So next we're going to move on to a different case study where we're now using a very common molecular sieve called zeolite 13X. So previously we were looking at a MOF structure, and now we're looking at a zeolite. These zeolites have a good benefit because they are very, very stable. We have a lot of sodium ions being joined with some of these aluminosilicate groups, and they're very, very stable. They can withstand very, very high temperatures. They also have a very well-defined pore structure. This pore structure is about 13 angstroms wide, and this has a very high surface area. Sorry, I said 13 angstroms. It's around 9 angstroms wide in a microporous material. This material has a high surface area. Because it has a high surface area, let's make an assessment whether or not this material is good at CO2 capture. So, like I did in the previous case study, I start off with the fundamentals. How good is zeolite 13X at absorbing pure CO2? So I do some CO2 isotherms at 60, at 40, and at 25 degrees C. And I can see this material has a good CO2 absorption performance at all of these temperatures. And then I can also, using these isotherms, give you the enthalpy of absorption. So how much heat is being given off as I'm absorbing all of these CO2 molecules. So this material is good at capturing pure CO2. I then have a look at the kinetics. I can see this material is also absorbing CO2 at relatively quick speeds at very low concentrations. And it's doing this at 25 degrees C and 40 degrees C. So I can absorb a lot of CO2 and I can absorb a lot of CO2 quickly. Now, let's look at this material in a co-sorption scenario. So now I'm going to look at 13X. How much CO2 did it absorb when it was dry? And this was a large amount. I have an uptake of around 21% CO2 when there's no humidity present. But if I now do an experiment where I first flow through just 5% relative humidity, and I maintain that relative humidity flow, and then start to change the CO2 concentration, now what I see is very, very different. When I have 5% relative humidity present, I can now see the mass of the sample barely changes at all when I introduce CO2. So it appears as if CO2 seems to have, or zeolite 13X seems to have lost its ability to capture carbon even just with a tiny amount of relative humidity present. And I can see as I'm scanning in CO2 concentration, the mass only increases now by 0.6%. So let's zoom in on the kinetic data that I can get from a gravimetric system. Now I can see this is the mass of the sample when it was activated. It then goes through a very big mass change when I introduce relative humidity. And then when I start increasing the CO2 concentration, the mass is barely going up. Now, it's quite interesting. If I zoom in on this area to a very small scale, what I can see is some interesting behavior. I can see that as I'm introducing the CO2, the mass initially increases and then shows a decrease. This is suggesting that I'm getting some sort of displacement going on here. So as I've introduced some of that relative humidity, CO2 comes in and we are now competing for some of that surface occupation, some of those surface sites within the material. So even though our material appears to selectively absorb relative humidity, on a very small scale, we do appear to have some displacement of water with some of that CO2 coming into the system. But as I mentioned in the previous case study, DVS is a gravimetric measurement. We are only measuring total uptake when we're letting in two things at once. So again, I need to go back to breakthrough analysis in order to tell me how much water and CO2 is being absorbed in these multi-component areas. So first, I may want to do these validation experiments. How do I know I can trust my breakthrough analyzer? Well, the easiest way to validate a different absorption instrument is to compare it with a validated one. So something like gravimetric data can be directly compared with breakthrough data for single component steps. So I can do breakthrough analysis at 10% CO2, 20% CO2, 30% CO2. I can measure their capacity, and then I can see how that compares to gravimetric data. So I can validate my breakthrough process by comparing it with gravimetric data. And we can see very good agreement between our single component breakthrough data and our single component DVS data. So now I've validated my breakthrough approach, I can use it to look at these multi-component scenarios. And when I look at the multi-component scenarios, I can confirm some of the conclusions I made in the gravimetric data. It looks like the zeolite 13X was mainly selectively absorbing relative humidity, which then prevented it from being able to absorb any CO2. And in the breakthrough analysis, I can confirm this. I can now see when I let in 15% CO2 and 30% relative humidity, both at the same time, what I can find is I have a very large uptake of relative humidity. Our millimoles per gram uptake is around 14.3. Whereas in the case of CO2, it's now at 0.2. So this is the only way I can definitely confirm that zeolite 13X will selectively absorb humidity over CO2. And that's because zeolite 13X is an extremely hydrophilic material. It's so hydrophilic that it will selectively and competitively absorb water, and that water has a precedence for absorption over CO2. So zeolite 13X is going to be very competitive in its absorption for water and CO2. So we've spoken a lot about relative humidity. Relative humidity is a very key area that we need to look at because water's everywhere. Often it is in direct air applications. It's in coal plants coming off the exhaust of a line. Water can be in a lot of these processes, and it's a very common contaminant. Now we're going to look at a slightly different contaminant, which we mainly find from these post-combustion processes. So that's going to be sulfur dioxide and nitrogen dioxide. So SO2 and NO2, these are produced from flue gases. Often fuel contains sulfur. When that sulfur is being burned in the presence of oxygen at some of these high temperatures, we're going to make small amounts of SO2. NO2 can be made just from the nitrogen in the air and the oxygen in the air at high temperatures. Or we may find that there's some nitrogen impurities in the fuel itself, and they are going to go through reactions with oxygen to form NO and NO2. So why is SO2 and NO2 so problematic for solid adsorbents? Well, SO2 and NO2, they are acidic and they're oxidizing gases. They are also able to form acids like sulfuric acid and nitric acid in the presence of relative humidity. So we can form acids, which mean a lot of our carbon capture processes actually need to be very corrosion resistant. Otherwise, they will degrade in the presence of these acid gases, which are very reactive. Now, they are very reactive. They can form very strong chemical bonds with some of our surface sites on the sorbent. And unfortunately, that NO2 and SO2 interaction with those surface sites is much less reversible than CO2. And that means we may be seeing some chemisorption. Chemisorption of this SO2 and NO2 onto these active sites may inhibit the performance of that material from capturing CO2 in the future. Now, we're going to use some of our instruments to assess the influence that SO2 and NO2 can have on a carbon capture material. So a lot of carbon capture processes, in fact, what they do is they will put in a flue gas desulfurization, which is basically a stack which removes NO2 and SO2 from the gas stream before it reaches my carbon capture material. Unfortunately, even with some of these flue gas desulfurization stacks in place, even after the flue gas desulfurization units, you will still have some NO2 and SO2 present. And usually they're in concentration somewhere between 10 ppm and 100 ppm. So even with flue gas desulfurization units in some of these processes, we still have a relatively high ppm concentration of SO2 and NO2, still reaching some of our carbon capture adsorbents. So we're going to design an experiment. This experiment is now going to be looking at doing some CO2 cycling at a concentration you would expect from a flue gas. In a flue gas, you may get something between 10 and 40% CO2 concentration. So we decided to do 10% CO2 cycles. And we've got a very consistent performance. We're getting a consistent uptake over 5 CO2 cycles. Then I want to reactivate my sample and I'm going to let in 75 ppm NO2. And that's a concentration that we might expect after flue gas desulfurization. And I'm going to wait for this concentration to completely saturate my sample of zeolite 13X. Then, after I have saturated my sample with 75 ppm of NO2, I'm then going to reactivate my sample and do the same CO2 cycles as I did before. And I want to see how much this contaminant has influenced the uptake performance from these compared to the before NO2 CO2 performance and the after NO2 CO2 performance. And I did this same experiment with 75 ppm of SO2. And what I can see, this is the average uptake pre NO2 or SO2 and post NO2 and SO2. And I can see very consistent performance between all 5 cycles. But after NO2, I saw instead of getting around 13.7% uptake from every cycle, I was getting around 10.82 CO2 uptake from every cycle. And that's a performance loss of around 21%. Now, in the case of SO2, that's far more impactful. I saw that after the cycles after SO2 exposure, my CO2 uptake is now 6.64%. So it significantly lost some of its CO2 capture performance. 52% of its capture capacity was lost after exposure to SO2. So we've made a very quick assessment that SO2 and NO2 can come into our carbon capture processes and it's going to prevent some uptake of CO2 in the future. So maybe one of the questions is, why can't I just remove that NO2 and SO2 thermally? And we made an assessment of that doing a TPD experiment in our DVS, which was thermally programmed desorption. So what I did is I activated my sample, I then introduce the 75 ppm SO2, and then I slowly heat that sample and see how the mass of the sample and the mass loss profile as a function of temperature. So what I want to look at is zoom in on how much the mass of the sample is decreasing as I am slowly heating up that sample. And I did the exact same for SO2 as I did with NO2. So overall, I could look at the uptakes during this experiment. I can see that after I did my SO2 adsorption, the total uptake was around 17.16%. And during reactivation, I was not able to go back to the same mass I had at the beginning. I had 5.3 weight percent still inside of that material, even after reactivation. And the same was seen with NO2, but to a lesser extent. When I went all the way up to 450 degrees C, I now had 2.01% weight percent remaining after exposure to 450 degrees C. So in both scenarios, I was not able to completely desorb the SO2. I was not able to completely desorb the NO2. That may be because we didn't go into a higher enough temperature. 450 degrees C is actually the maximum temperature we can go in the DVS carbon. But I was unable to remove all of that SO2 and NO2. Now, what I was able to do is I was able to plot some of the mass loss as a function of temperature and look at the DMDT. So effectively, what was the rate of the mass loss as I was scanning at a linear ramp rate? Now, as I was going up from 25 degrees C to 50 degrees C, not a lot happens. And then when I start approaching, 90 degrees C, that's where the mass of the sample starts to drop more significantly. And that's where I get a peak in my DMDT. The rate of mass change increases quite suddenly. Once it's increased quite suddenly, it then begins to decrease more slowly and slowly. Now that gives me an indication that around 90 degrees C, I was able to lose some of that more weakly bound SO2. Now there is no other peaks forming as I go to these higher and higher temperatures, which means I was only really able to remove some of the weakly bound SO2, and some of the more strongly bound SO2 remained within the sample. With NO2, a similar process happens. We lost some of our NO2 at some of these lower temperatures. Then it begins to slow down. And then I see another peak forming around 255 degrees C, where I was able to lose some of the NO2, but I was not able to lose all of the NO2 up till 450 degrees C, as my sample did not go back to its initial mass. So, to summarize, this case study has shown that SO2 and NO2 can have a significant impact on our materials. They can prevent uptake and change the kinetics for CO2 after their exposure. And we can look at what temperatures can desorb some of that NO2 and desorb some of that SO2. And what's needed in order to activate those materials after exposure to SO2 and NO2. So we're going to look at some final case studies in our last 20 minutes, which is going to be looking at, instead of moving into carbon capture, now looking at capturing VOCs and looking at indoor air quality and using porous materials to capture some volatile organic compounds from the air. So what is a volatile organic compound? A volatile organic compound is an organic chemical that can easily turn into a vapor at room temperature. They have high vapor pressures, meaning that they can populate the air in large concentrations, and they disperse into the air relatively quickly. So, toluene is a very popular VOC. It's used in a lot of industries, things to make glues, paints, inks, and it's got a very large market size. VOCs actually have a very negative impact on our health. They can cause numerous lung damage, some diseases, and they can intrude with a lot of our processes. they could be toxic at incredibly small concentrations. So we need to find porous materials that can capture very common volatile organic compounds from the air in order to prevent some of these bad issues that we may find with our health. So indoor air quality is actually a very increasing area in the porous material space, being able to scrub the air to make it safer for everyone. And we're going to look at some case studies using very popular adsorbents in how well they can capture some of these VOCs. So using porous materials to manage indoor air quality. And again, we're going to be looking at things like zeolite 13X and activated carbon. So first, we're going to do like what we did before. Look at the single component isotherms for these materials. This is going to be looking at toluene. And what we notice with zeolite 13X and toluene is at a very small concentration, we have a very significant uptake. So even at these tiny concentrations of toluene, we're getting a very high uptake. We're seeing really, really large uptakes from in the tens of ppm level. And then when we increase that concentration to higher, it goes up in this stepwise fashion. We can do the same for zeolite 13X and water adsorption, and it's a very similar scenario. At very low relative humidities, we almost completely saturate zeolite 13X. So we can see that this material can absorb a lot of toluene and it can absorb a lot of water. Now let's look at something like activated carbon. Activated carbon, quite similarly, it can absorb a lot of toluene at low toluene concentrations. So as little as 1000 ppm, we are getting a mass change of around 25% increase in the mass change from low concentrations. So again, activated carbon has a high toluene uptake. Activated carbon also has a high water uptake. But what we can notice is it's fairly hydrophobic at low relative humidities, but then it shows high uptakes at higher relative humidities. So we're seeing some of their pores within activated carbon begin to fill as we go to some of these higher relative humidities. But at low relative humidities, uptake remains relatively low. So this is a case study where we have taken a lot of porous materials and we have assessed what they have been like in their single component isotherms and then look at their performance in true multi-component settings. So we have things like activated carbon, amorphous silica. Activated carbon is shown in the orange triangles. Here we can see it's our isotherm for toluene, for water, for butanone, and for ethanol. We can also see zeolite 13X. That's the thing shown in the red boxes here. And we can see we characterized all of these materials for their single component isotherm for water and a variety of different volatile organic compounds. But we're going to be focusing on zeolite 13X and activated carbon. So now what we want to do is rather than look at their single component isotherms, we want to see what's their performance look like in real world conditions. So in the true multi-component steps. So here we have our activated carbon. We are first letting in, we're equilibrating with relative humidity. Then we are adding some toluene. So at the same time, so this is a co-sorption step. Then we remove the toluene and we remove the water. Now what I can notice for this activated carbon sample is it absorbs a bit of water. Then when I let in some toluene concentration, it absorbs a lot of toluene. So activated carbon appeared to have a good performance in the presence of a low relative humidity. So at 25% RH, this material was able to maintain its co-sorption, its working capacity for toluene in the presence of relative humidity. Now, in the case of zeolite 13X, we first let in relative humidity. It has a high uptake of around 22%. Then when I let in the toluene, I can see barely uptake when that toluene is present. In fact, here is a zoom in here. We get a small amount of toluene absorbed, but we can see it's very small in comparison to what we find in the case activated carbon. And that's what's being plotted here in this data. Here we can see the single component uptake, which is effectively how much toluene was absorbed when there was no humidity present. And that's what's being shown in white. We can see activated carbon actually had the best performance for toluene uptake at dry conditions compared to 13X or compared to some of our Y-type zeolites, our Z-type zeolites and amorphous silica. It had the best performance, but we can see as we go to higher and higher relative humidities, activated carbon actually begins to have worse and worse performance. In the case of zeolite 13X, it's only able to maintain any toluene uptake in dry conditions. As soon as you go to any relative humidity step, it has no toluene uptake whatsoever. We can also do this in a slightly different way. So now we will be holding the relative humidity constant, and we're going to be doing a few toluene adsorption cycles. And we can see in the case of activated carbon, it has a very good uptake in its first absorption cycle, but that begins to decay after its last few cycles. The same can be seen in the case of zeolite 13X, which means some of that toluene may be strongly absorbing onto the surfaces of these materials, preventing them from reactivating and having a higher uptake on their subsequent cycles. And we can see the same effect being seen at when relative humidity is introduced. In 50% RH, in the presence of 50% RH, activated carbon maintains some of that toluene capacity, whereas zeolite 13X loses a lot of that toluene capacity overall. So a lot of this was done in a gravimetric instrument for this study we see here. All of this was done in a gravimetric instrument. Now let's look at the true multi-component data in something like a breakthrough analyzer. So in the breakthrough analyzer, we again took zeolite 13X. We took this was in a pelletized form. We took 190 milligrams and we loaded it into our glass column, just like you can see here. And then we're going to introduce a gas concentration over this column and see when it hits our detectors. So we first activated it at 300 degrees C under nitrogen at 200 SCCM. We then let it cool down to our absorption temperature of 25 degrees C, and we let in a feed gas of 823 ppm of toluene. We then wanted to do another feed gas, but under wet conditions. We then regenerate the material in a similar condition to its activation, so 300 degrees C of nitrogen, and we let it cool back down. And this is going to give us our absorption capacity, but instead of measuring the mass change to measure absorption, we're going to be looking at the amount from breakthrough analysis. And here I can see the toluene absorption capacity from 820 ppm is around 1.95 millimoles per gram, or 17 or 18% weight capacity. And this is from a number of different cycles that we've done. And we can see a consistent performance over 3 cycles. Now, what we can do in breakthrough analysis is we can look at the adsorbed amounts by looking at the absorption breakthrough. And we can compare that to doing breakthrough, but now through the desorbed capacity. So heating up my sample, that's what's being plotted here, heating up my sample to 300 degrees C and looking at how much toluene is hitting my array of sensors. And the area under this curve is telling us how much toluene hits the sensors in total, how much was absorbed on the sample. So I get the desorbed capacities, and we can see these desorbed capacities have a very good relationship with the absorbed capacities. And when these match, we can really be confident in our results. Now let's do these multi-component breakthrough experiments, where I am letting in both relative humidity and 815 ppm of toluene simultaneously. And what I notice is I will first have a certain amount of toluene breaking through my process. And then I can see that toluene breaks through first. It experiences some roll up and then comes down to 815 ppm. So this material absorbed toluene, went through a roll-up step, and then equilibrated. Our relative humidity broke through a little bit later to 30% RH. And really what this is telling us, the fact that we saw such a significant roll up to such a high concentration is telling us that a lot of this toluene had been displaced by the water that had come through. And when we calculate how much toluene was actually absorbed in the presence of relative humidity, you can see it is in fact very, very low. So we can see that in the case of zeolite 13X, we have a very low toluene uptake capacity and a very high relative humidity capacity. So we now can see that this material will again show competitive adsorption. It will selectively bind to water and has a precedence over water absorption when compared to organic vapors like toluene. And here is just a summary of the adsorption capacities as a whole. We can see under dry conditions, very repeatable performance, but under wet conditions, we can see a less repeatable performance in the case of relative humidity being present. So unfortunately, zeolite 13X does not look like it would be a good material for looking at managing indoor air quality, because any humidity present would mean it has no ability to absorb toluene. Something like activated carbon, which is more hydrophobic at low relative humidities and has a very strong uptake for something like toluene, may be a lot better for making a porous material for managing indoor air quality. So we only have about 8 minutes left. I may very quickly go through our final few slides, and then we can open up to a Q&A. So I'm just going to breeze through these slides for the last few. So we're going to be looking at making a MOF that can be used as a sensor for detecting very, very small amounts of volatile organic vapors like toluene, or some more exotic volatile organics that we may find being formed in space applications. So we want to find a porous material that can measure incredibly small concentrations of some of these VOCs. And we want to be looking at ppm level or even lower, ppb level. You can imagine if we are in reduced pressure environment you would see in space, the concentration of some of these organic vapors are going to be very, very small. And we need to have a sensor which is incredibly sensitive to the low level of these volatile organic vapors. Now, there's a few different ways we want to detect parts per billion or parts per million concentrations. We can use something like FTIR, gas chromatography, mass spec, photonionization detection. They are very, very accurate and very, very sensitive, but we don't get immediate real-time data. Or we can use, and they're relatively bulky and difficult to miniaturize to put up into a space application. Or we can use something like on-site detection, where we can have a miniaturized technology which is cheap, small, and real-time. And that's where using something like a microbalance that we may find in something like a sensor, or a balance that we have within the DVS, we can use this to be mount our porous material on top of and see the mass change in order to detect some of these VOCs in our process. Now, in this project, which was actually performed by my manager at his time in his PhD from the University of Montpellier, and that's Dr. Paul Iacomi, he was part of this publication from IGCM. And in this process, they went through a set of computational experiments where they were screening a number of MOFs that existed on the core MOF database. They went through a number of screening steps, which was looking at these 14,000 MOFs and wanted to slimline them to have a pore size of which is greater than 6 angstroms. They needed to make sure that there was the correct enthalpy of adsorption of some of these VOCs, so they were hydrophobic enough. They went through a few different performance rankings of their isotherms, and they narrow down their MOF selection to a select few. Now, what we want from these MOFs is effectively them to absorb reversibly, these VOCs, so that they have a long lifetime. They want them to be thermally stable. They want them to survive the pressures and the conditions of space. And they want them to be able to measure these small ppm concentrations or ppb concentrations. So a variety of these MOFs that were screened computationally were placed onto a sensor which was on the microbalance. So the microbalance is going to be measuring how much that MOF is changing in its mass, which we will assume is from adsorption of volatile organic vapors. In this project, they used a DVS vacuum, which is placed in IGCM. They used a MOF, which is MIL 101, and they want to be measuring very small concentrations, so parts per million, parts per billion of small concentrations of some of these gases. So MIL 101, mesoporous MOF, which was slightly modified, was able to measure incredibly small concentrations in the parts per billion of siloxanes, things like D4, in relatively small time steps. So in a step which is only 50 minutes or so, we can see very increase in the mass that we were measuring of these samples. We can see a slightly different sensor made for DUT4, which is now more optimized for toluene absorption. Again, if we look at the pressure we are measuring here, we are at 0.002 P over P naught, which again is in the parts per million range, 25 ppm, 50 ppm. And we are using a microbalance to measure the uptake on extremely small concentrations at reduced pressures. And again, another MOF, which is MOF 74 with nickel metal groups, now being used for phthalate detection. And we can see a very sharp increase in its isotherm shape, which shows that it has a high affinity for this organic volatile, this VOC, at these low concentrations. So, sorry, I went through that last one a little bit quick. We were coming to the end of our time. So in this final case study, we've screened a lot of porous materials in order to find a porous material appropriate for VOC capture. We tested them under realistic conditions we would expect to find in space applications, space exploration applications, and we've found a few promising sensors which can be placed onto microbalances for sensing very small concentration of these VOCs. With that, I'd like to thank everyone for coming to today's webinar. We had a great attendance. I think at maximum, I saw there were around 72 of us. So thank you everyone for coming. I want to say a big thank you to all of our internal and external collaborators, especially those from Imperial College London, from NovaMOF, from IGCM, and for some of the funding sources for some of the projects that were done there. I'd like to say a big thank you to my manager, my mentor, Paul Iacomi, and thank you everyone for coming today. I'd love to open up to some questions.
Thanks, Connor. Thanks. That was a great presentation, very in-depth. We've got a few questions that have come in. Paul has thankfully been answering some of these queries, but we'll leave the screen with you in case you want to reference back to any of your slides to answer any of these questions. I've picked out just a few of the questions that I thought would be useful to share with the whole meeting. So the first one that came in quite early was, what's the operating temperature range for this equipment, and can it be used to obtain specific surface area?
Yeah, a lot of our instrumentation does have a wide variety of temperature operations. Most of our DVSs work between 5 degrees C and 85 degrees C. That's the incubator temperature. But we can go to much higher temperatures around the sample for things like activation. So for things like the breakthrough analyzer, this can go all the way up to 500 degrees C. In some of our other instruments, it's 400. In some of them, it's 200. So we have a wide range of temperatures that our instruments can take, but have a look on the brochure for the specifics of what temperature range is achievable. Now, surface area can be measured in a few of our devices. Generally, if they can absorb organic vapors, things like octane, we can do the BET measurements instead of using something like nitrogen, which is commonly seen in volumetric instruments. We can use organic vapors like octane to make surface area determinations. And this can be done in any DVS, which can work with organic vapors, or with something like our IGCSEA, which I didn't have a lot of time to talk about today.
Right, thank you. Another question here. For the post-combustion carbon capture using the MOF, is it from a natural gas power plant flue gas? Do you have the presence of oxygen that could be detrimental? And how do you pressurize the flue gas before carbon capture?
So yeah, it's important to note that in everything we showed in the work today was performed inside of these instruments. And inside of these instruments, we generate our own gas mixtures. So the user is responsible for selecting relative humidity, CO2 concentrations, and then we also can put in things like SO2 and NO2. We are not directly using a flue gas from a plant. We're not plumbing that directly into the device. Instead, we are simulating that environment by building the gases that go into that flue gas. So most of the experiments we showed today, they were done in a nitrogen atmosphere. But we would have had the option in some experiments to use air as our gas or to introduce oxygen. So our instruments can simulate some of those post-combustion conditions. We just have to be quite specific into what we're letting in. If I let in 4 reagents which can all absorb at the same time, sometimes it makes some of the data processing and what's actually going on with the sample a little bit more tricky to work out. So in a lot of what we showed, we were simplifying it to a co-sorption scenario with just water and CO2. So to make the experiments a bit more simple in its approach. I hope that answers the question.
Great, thank you, Paul. Connor. In the case of NOx and SOx, instead of using FGD before carbon capture, why not use enzymes to reduce the energy penalty?
So it's an interesting proposition. SO2, the SO2 and the NO2 will be binding to some of the metal centers very deep within the porous material. These SO2 and NO2 will bind very, very strongly. The enthalpy of that interaction will be very, very great. It's a strong chemisorption bond. We also need to remember that in the flue gas stream of some of these coal plants, they're in very extreme conditions. I believe enzymes may not be the most appropriate and may denature and degrade in the presence of such high temperatures, in the presence of acid gases, oxidizing agents. So I believe that enzymes may not be the most suitable technology for application in these conditions.
Right, thank you. So someone's just asked to clarify. So the DVS, or which instrument is able to perform the breakthrough at different relative humidity of various gases?
So our DVS line, this was not the experiment. These were not the instruments that did any of the breakthrough experiments. The breakthrough experiments were performed in the breakthrough analyzer. So the BTA Frontier, this device that we see here, this was the one that did all of those breakthrough experiments. In a lot of I'm sorry if I didn't make that as clear during the presentation. A lot of what I was presenting was both DVS data where stuff had a mass change, but basically all the other things that were working out uptakes not with mass as one of its units, instead with things like using a chromatographic technique with a breakthrough curve, that's exclusively being done in the breakthrough analyzer.
Right, thank you. And then the final question here, can you work with nitrogen in that device at -200 Celsius?
Unfortunately, none of our devices go to the cryogenic temperatures. All of our devices have a minimum temperature that we can reach at around 5 degrees C. So we can't go sub 0 degrees C in any of our instrumentation.
Great, thank you. I think that's the last of our questions, and we're now 5 minutes over time, so we might be distracting people from their next meeting. So I think we'll leave it there. Thank you once again so much, Connor, for the presentation today. Really in depth and really enlightening.
Okay, yeah, thank you everyone for coming. Thank you, John, and enjoy your day.
Yeah, another thank you to our audience. If you do have any questions, please do reach out to us at info@surfacemeasurementsystems.com, or you can find out more information about all these instruments at www.surfacemeasurementsystems.com. We will be making today's recording available in the next few days for those who would like to refresh their points on anything. But just before we close, I'd like to draw your attention to the Sorption Hub. Now, this is a free online portal for our users or anyone just interested in sorption science and our instruments. You have a full catalogue of courses in the e-learning section, as well as full access to our application notes and brochures. There's also a help desk and a consumable store that you can use if you are one of our instrument users. So please do go to www.sorptionhub.com and sign up now for access to the e-learning, help desk, and consumable store. It's all completely free. You just need to request a login. I'd like to thank everyone again for attending once more, and please do enjoy the rest of your day wherever you are.